Alright, so in the previous video, we spoke at great length about this process of finding what an antiderivative was using this new symbol for the first time in your mathematical careers known as an integral, but we didn't really speak at any point about what the heck does that actually mean. So, when we are performing this process of integration, we are taking some type of function, f of x, and what integration is doing is, let's say we have some bounds a, some bounds here, b, right? It is infinitely be here forever. Right. It is infinitely chopping the area beneath the curve. Right? So we are summing the area beneath the curve using an infinite number of rectangles, right? And I can be here forever, but just so I don't bore you on this video, okay, just imagine I had sat here and drew as many tiny rectangles as I could. Now, what's really happening? Okay, well, the distance between the rectangles is known as delta x sub I, right? Because we have so many we have rectangle 1, 2, 3, 4, 5, 6, 7, 8, you know, so on and so forth. Okay, delta x is really representing the width, right? So, you know, this could be, you know, 2.4, 2.3, right? So we got 1/10, okay? And then our outputs we'll just know as f of c sub I, but that is representing our length, okay? And what integration is doing, right, so this idea of a definite integral is the definite integral of f of x over ab denoted by the integral sign is the limit If you've been with me throughout this entire video series, the first thing I said in my first video was what is the purpose of Calculus 1, right? It's this exploration of limits, and look, now that we're touching upon the final topic in our Calculus 1 exploration, limits once again play a key role. The limit of Riemann sums. So I reserve the right of your professors in the fall to explore those Riemann sums at great length. If you've taken AP Calc before, you've already done it using, you know, the trapezoid rule, the midpoint rule, etc., etc. But because we have such a condensed amount of time, I don't spend a lot of time talking about that. But okay, when we have a definite integral, so the integral over a closed bounds from a to b of a function, what's really happening, okay? So what you'll be actually doing kinesthetically, and if you were to type this into, you know, some type of mathematical software, we're really taking the limit as delta x sub I approaches 0. So as this width gets smaller and smaller, so as we start to increase the amount of rectangles that we are summing underneath this curve that is equal, or sorry, we're taking that limit and we're summing, right? So this is the symbol for sum as I goes from 1 to n of f of ci, which is the length of each rectangle, times delta xi, which represents the width, right? So as we get closer and closer to 0, the number of rectangles seemingly increases infinitely, and we continue to sum and add and add and add those rectangles. However, you should notice that this function is completely above the x-axis. So what do we do in the instance when we have something like this? A, B, and we're tasked with determining what the value or what the area is under the curve for this function. However, the area under this side of the curve is clearly positive, but this area here, is this negative, or is this, or do we treat this as positive still? Well, we call this a situation of signed area, where what we really want to do is we want to take the area above the x-axis, which we know will be inherently positive, and we want to subtract it from the area below the x-axis, because if we treat that as inherently negative, well, subtracting a negative will ultimately yield a positive, therefore we are adding those two values regardless. Now, let's take a look at this. Let's say we have this area here from 0 to 5 of 3 minus x. Before we look at this graphically, let's just take care of this on our own. The antiderivative of 3 will be 3x. The antiderivative of x will be x squared over 2 from 0 to 5. If we substitute these values in, this becomes 15 minus 12.5 minus 0. Right, because 0 would be the terms there. So this really gives us a 2.5, or 5 halves. If we graph this, this is a very straightforward graph, hence why we're using this type of example. Right, 3 minus x, we have a slope of negative 1 starting with a y-intercept of 3. So 3, 2, 1, 1, 2, 3. And we're going from 0 to 5, so that puts that there. And at 5, that puts me down here. So our graph looks something like this. So notice the area under the curve includes this space as well as this space. Okay. If geometry taught you anything, it should tell you how to identify shapes. So we have two triangles here. If we take the area of triangle 1, we get 1/2 times base 1, 2, 3 times height 1, 2, 3, which is going to yield 9 halves. So far so good. And we get the area here, which is 1/2 base 2 times height, also 2. Right? These will cancel, so we have 2. We take 9 halves minus 2. You can see that we get 5/2. So, going back to my previous point, I finally remember saying that if we treat it as inherently negative, we'll have a minus and negative, which yields a positive. So, but we don't want to do that actually, okay? Because the good thing about the definite integral is that signed area is pre-programmed into the definite integral. Right, so when we take this area above the x-axis, right, which is inherently positive, and we subtract it from the area below the x-axis, that area below the x-axis area, we're treating it as a positive ideal, positive concept, okay? So we're taking two positive values and we are subtracting them. We're just making sure that we subtract the area beneath the x-axis from the area above the x-axis, not vice versa, or else this would turn negative, and that really can't happen. But when we're not looking at it graphically and we're just computing a definite integral, we don't even need to worry about that at all, because signed area, once again, is pre-programmed into the definite integral. If we wanted to take a look at the integral of a constant, okay. So think about this graphically as I'm erasing. What would the area beneath a constant function look like? So integral of a constant. So let's say for any constant c, the integral from a to b of c dx. Alright, so let's say we have some arbitrary value c. We're looking over it from this interval a to b. But remember, we are summing the rectangles. Well, if I have from a to b, here's my width, right, and here's my length. But my length is really equivalent to whatever value c is, and my width is really equivalent to whatever the difference of these two values is. So I have length times width. Let's get a practice problem in. Definite integral from 0 to 3 of 2x squared minus 5. So if we integrate this, once again, we're going to add 1 to the exponent, x cubed, and divide, minus, there is no variable here, therefore it was a x before from 0 to 3. Okay. We're going to take the rightmost bound, substitute it, 2/3 times 3 cubed minus 5 times 3 minus, right, pre-programmed. Oh, this is going to be 0 minus 0, so we just put a 0 here. Okay. 3 cubed divided by 3, that's going to be 3 squared, that's 9, 18 minus 15 equals 3. So this function, 2x squared minus 5, a parabolic function opening upwards, starting with a minimum value of negative 5, from 0 to 3, has a signed area of 3. What happens though in the event you have a graphical situation that unfolds like this? You have the integral from b to a of f of x dx, but b is greater than a. Okay, we can't go backwards. So what we do is we remove a negative, which allows us to reverse the limits of integration. So your larger bound must always be the top value of the integral, never the bottom value. Right, and This is for when a is less than b. So if your smaller bound is located at the top, you must rewrite or reverse the limits of integration and rewrite that lower bound from the topmost position to the bottommost position. And you might actually wind up in a situation, typically a piecewise function, where you could have something like, okay, notice two different function behaviors. Let's call this A, let's call this B, let's call this C. Okay, we can't simply say, oh, take the integral from a to c of f of x dx. And why can't we do that? Well, it's not f of x the entire way throughout. But what we can do is we can split this, say, oh, I'm going to integrate this function from a to b plus this section from b to c. Now we'll still call it f of x because typically it's a piecewise function, and piecewise functions don't have multiple function names to them, right? But you may also split your intervals so long as there's some type of seamless transition or seamless swivel point. And that'll do it for our discussion on definite integrals. Next up, for the calc, the fundamental theorem of calculus, part 1.